Today again we will be arriving 20 minutes ahead of schedule.
Whatever happened to TriJet airliners? There was a period when the classic three-holer was a common sight at airports around the world. McDonnell Douglas DC-10s, Boeing 727s and their like dominated the skies on domestic and international routes the world over, providing a unique silhouette that's virtually disappeared from commercial aviation. So where did they go? And importantly, why did the TriJet evolve in the first place? Well, to understand this, we need to examine a particular period of airliner development between the late 1950s and early 70s, commonly called the Golden Age of jet travel, when all kinds of advanced concepts were being tried on commercial jet airliners. 2 engines were good. But 3 engines, well, they were better for airlines wanting more from their jet airliners while remaining in keeping with federal regulations. Not only was the new layout beneficial for operators, but it added a striking new look to the skies. The TriJet was a distinctively different profile, and it became an icon when it appeared on airport tarmacs throughout the ever-so-fashion-conscious 60s, 70s and 80s. Quite coincidentally though, a new type of commercial jet engine was born to propel increasingly bigger aircraft into smaller airports more economically, which offered legitimacy to the TriJet, the bypass turbofan engine. Their stories are interlinked, and yet this icon of the golden age has all but disappeared in the 2020s. Where did they go? Ladies and gentlemen, I'm your friend Mike Brady from Airliner Designs, and this is the story of the rise and fall of the TriJet airliner. 3-engine airliners were not just a product of that golden age in the mid-20th century. In between World War I and II, there were a number of aircraft manufacturers whose ambitions were constrained by the power output of aircraft engines being produced at the time.
So heavy, the huge wheel crushes the pavement and sinks.
When 2 piston engines were not enough, commercial aircraft companies like Fokker in the Netherlands, Ford in the US, and Junkers in Germany had found that fitting an extra couple of engines to existing aircraft enabled them to increase their load lifting capacity across greater distances. And importantly, in those early days when air accidents were unfortunately a routine part of air operations, it increased their reliability. Multi-engine aircraft had first appeared during World War I, and consequently, the aircraft produced were lugging high explosives around rather than passengers. The first trimotor to successfully fly was the Italian Caproni CA-1 long-range bomber, which took to the sky for the first time in 1914. Once the fog of war had cleared, many of these pioneering strategic bombers, like the Farman Goliath and the iconic Handley Page HP 0400, had their bomb bays removed and their fuselages filled with seats instead. In the burgeoning years of air travel, airframe and engine development scarcely ran parallel to one another. And technological innovation in one field, say in passenger comfort through fuselage design, didn't necessarily mean that a power plant capable of lifting that entire aircraft into the air was yet available, and vice versa. This meant that a range of airframe and engine configurations, some conventional, some forward-thinking, and some downright bizarre, were considered, as manufacturers struggled to match growing airline and passenger expectations. Of course, the biggest issue for operators was one of reliability. It was all very well running an airline, but if aircraft weren't able to remain in the air for long because of unreliable engines, then the entire operation was pointless. The solution was often to add more engines, and the 3-engine airliner was born. The first trimotor to see widespread use was the Fokker F-7B-3M, a high-winged monoplane that first flew in 1924 as a single-engine aircraft. But it had 2 more engines added, one under each wing, to become one of the most widespread commercial airliners of the 1920s and early 30s. Designed by Walter Rettel and supervised by Reinhold Platz, Fokker's chief designer had brought to life a range of formidable single-seat fighters for the Germans during the war. The Fokker F-7B-3M incorporated technology that was first applied to those Fokker fighters: wooden box spar wings, welded steel tube fuselages covered in wood and fabric. Powered by 3 220 horsepower Wright Whirlwind engines, and capable of carrying between 6 and 12 passengers, the Fokker's origins come from the 1925 Ford Reliability Tour, launched by Edsel Ford in the United States as a means of increasing reliability in air travel. While he was living in the USA, Anthony Fokker got wind of this and instructed Platz to simply add more engines to the already in-service Fokker F7. The Fokker Trimotor became an instant hit, completing the 1900-mile circuit of the Reliability Tour, around the northwestern United States with a perfect score in the points allocated competition. On top of that, the F-7B-3M saw service on every continent, spanning oceans and crossing deserts, with licensed production in 7 different countries. It's fair to say that the Fokker Trimotor was the world's most popular airliner of the late 20s, but its distinction didn't end with commercial aviation. The type was used by many adventuring aeronauts, including Australian Charles Kingsford Smith, who was the first to fly an aircraft, his F-7B-3M Southern Cross, across 7,200 miles between the USA and Australia. The Fokker Trimotor was also the machine in which Amelia Earhart was a passenger across the Atlantic between Newfoundland and Wales on June 17, 1928, in an aircraft owned by famed explorer Richard Byrd, that he was going to take on his expedition to Antarctica the same year. Byrd's Trimotor, Miss Josephine, was his mount on his controversial 1926 Arctic flight to the North Pole, whose outcome has been questioned ever since. But 2 more Trimotors from this exploratory era of aviation are definitely worthy of mention in this story. The first is the all-metal Tin Goose, the Ford Trimotor. This boxy-looking beast resembled the Fokker Trimotor, but for one important difference: its corrugated sheet metal outer skin. Although the Ford Trimotor wasn't the first all-metal trimotor airliner, that honour goes to the German Junkers G-24 that debuted 2 years earlier, the Tin Goose was designed simply and was noted for its reliability and its ease of servicing in the field. Its rugged construction saw it adopted as a hard-working freighter in less developed regions like Papua New Guinea and Central America. Although not as widespread around the world as the Fokker Trimotor was, despite being manufactured in large numbers, the Ford was an important aircraft in the annals of aviation history because of that reliability, which boosted the popularity of the Trimotor as a design choice available to commercial aircraft designers around the world. This would of course come back during the jet age, but hold on, we're getting there. In the United States though, the dominance of the Trimotor ended abruptly because of one accident that claimed the life of a national hero. On March 31st, 1931, a TWA Fokker F-10 crashed shortly after departing Kansas City Municipal Airport on its way to Los Angeles. On board was football great and coach of the Notre Dame Fighting Irish team, Knut Rockne, who, along with the aircraft's 7 other passengers and crew, perished. The cause? Delamination of the Fokker's one-piece wooden wing owing to moisture ingress over time. The public outcry over the accident was considerable, the immediate impact of which was caution from the travelling public toward the Trimotor configuration. Despite the causal factor being the wooden wing of the Fokker, not the engine arrangement, the all-metal Ford wasn't immune to the prejudice, as passengers demanded newer, safer airplanes, and importantly, ones that didn't resemble the staid-looking Trimotors. This single accident sent shockwaves through the US aviation industry that resulted in a new generation of airliner, the all-metal, low-wing, continent-spanning, twin-engine monoplane. These became the icons of the 1930s. Just think, the elegant Boeing 247, followed quickly by the Douglas DC-1, the DC-2, and then the sleeper transport, the genre-defining DC-3. The Trimotor's day, it seemed, was over. In distant Europe, however, the Trimotor remained a staple of commercial aviation for longer than in the USA, as pioneers of all-metal aeroplanes, Junkers, based its structural designs on a simple, strong, and durable philosophy. The aircraft's outer covering was a load-bearing structure stiffened by a corrugated external surface, which required less internal framework, thus reducing structural weight and enabling the carriage of increased payload weights compared to their contemporaries. Junkers aircraft proved extremely rugged and dependable because of this. The first was the very first all-metal commercial aircraft, the F-13 four-seat airliner of 1919, which was followed by a family of aircraft bearing the same Junkers hallmark of angular looks and wrinkled skin, culminating in the iconic Ju-52 3M. The second Trimotor worth mentioning, and one of the world's most notorious, the Ju-52 was the transport airplane of choice for the invading German armies before and during World War II. Although seeing a mundane existence hauling passengers on mainstream routes across Europe with German national carrier Lufthansa, it was the Third Reich's adoption of the type as a bomber transport and its controversial use in the Spanish Civil War that put the Ju-52 into the headlines. Nicknamed Auntie Junkers or Tante U, the Ju-52 was soon joined on the battlefields of World War II by a series of Trimotor airliners converted for war purpose from Italy, the most famous of which was the Savoia Marchetti SM-79 Sparviero. This unusually fast aircraft, like the Ju-52, began life as a commercial transport capable of carrying 8 passengers. First flying in 1934 and just missing the McPherson-Robertson England to Australia air race for which it was actually designed, the Sparrowhawk was a speedster, achieving a number of distance and time records for an aircraft in its class. But just like the Ju-52, its main claim to fame was as a warplane. It was the Reggio Aeronautica's premier bomber on the entry of Italy into the war in 1940. Despite the Sparviero's impressive war record and Italy's widespread adoption of 3-engine bombers and transports throughout the war, it was the only major participant of World War II that actually continued with trimotors. This was because Italian aero engines didn't progress beyond the pre-war years, whereas other nations' manufacturers built bigger and more powerful engines fitted with superchargers, turbochargers, and other innovations that stretched reciprocating engine technology to its absolute limits. Italian trimotors were the last of their breed in military service. There simply wasn't a need for them anymore. With ever-increasing technological advances spurred on by the necessities of war, the trimotor disappeared in the immediate years after World War II. The new generation of modern airliners like the Douglas DC-10 and the beautiful Lockheed Constellation used 4 engines to span the world's longest air routes, while surplus twin-engine C-47 Dakotas had shorter regional and domestic routes all sewn up. The first new-build regional airliners post-war, like the Vickers Viking, Ilyushin IL-12 and the IL-14, had large capacity engines, tried and tested in the crucible of war, which really negated the need for a third. It seemed that the trimotor was well and truly dead, but there was light at the end of the tunnel for the configuration with the escalating development of the gas turbine, whose early reliability and power output was a little suspect. This created, weirdly, a similar situation as after the end of World War I, where engines and airframes seldom matched and neither were able to exactly meet the needs of what the operators actually wanted from them. The first jet-powered airliners in service were nominally 4-engine because of the added safety margins. There was regulatory impetus behind the number of engines too. In 1953, the US Civil Aeronautics Board, the predecessor to the FAA, introduced what became known as the 60-minute rule. This said that an aircraft with less than 4 engines had a maximum time of a 60-minute diversion to the nearest airport in case of engine failure. This was simply a safety mechanism established because of the dubious reliability of piston engine airliners, but it also applied to jet aircraft, owing to their commercial infancy. While jet engine reliability did increase over time, these first-generation jet engines were gas guzzlers that necessitated airliners making multiple refueling stops across long-haul routes. Clearly, a solution to the pure turbojet's thirsty habits was required. To discuss this, we need to dive into the intricacies of the jet engine. Gas turbines work on basic Newtonian theory, specifically Newton's third law of motion, in that for every action there's an equal and opposite reaction. In a jet engine, this means accelerating a mass of air rearwards at high velocity will create forward momentum. This is thrust, or the expulsion of exhaust gases, creating a reaction force that propels the aircraft forward. The principle of operation of a gas turbine engine is through a continuous flow thermodynamic cycle, which is known as the Brayton cycle. The Brayton cycle, or the constant pressure cycle, because pressure is generally constant as gas volume and velocity increase, works across 4 distinct stages: intake, compression, expansion or combustion, and exhaust. Breaking this down, the engine draws in air through the intake into the compressor section, which compresses the air, thus decreasing its volume but increasing its pressure and temperature. In the combustion section, the air is mixed with fuel and its volume and temperature increases, while pressure remains relatively constant. This heated gas, produced during the combustion stage, expands and accelerates through the turbine, after which it's directed out the exhaust section at high velocity and temperature and decreased pressure. This produces thrust. Now, this description also depicts the basic structure of common gas turbine engines, which normally comprise 5 basic sections, including the intake section, the compressor section, both of which are referred to as the cold section of the engine, then the combustion section, the turbine section, and the exhaust section, which comprises the hot section of the engine. The biggest advantages between the gas turbine and the conventional reciprocating or piston engine are its propulsive efficiency. That is, the engine's ability to just produce sufficient power at different aspects of the aircraft's flight regime. gas turbines produce relatively constant thrust at high velocities, whereas reciprocating engines reduce in efficiency as velocities increase. Gas turbines' power-to-weight ratio, that is, the amount of power actually produced for a given engine weight, is more efficient than a reciprocating engine. Gas turbines also offer improved reliability, owing, believe it or not, to fewer moving parts, which offers less vibration and wear, resulting in longer times between servicing. The disadvantages of gas turbine engines over reciprocating engines are the high temperatures required for increased thermal efficiency. This requires specialist materials in their construction and creative means of internal cooling of components to prevent them from straight up melting. This leads to the expense of developing high-strength alloys and the specialist manufacturing of components within the engine. This complex set of circumstances caused reliability issues with the first jet-powered aircraft, especially the Messerschmitt Me-262, whose Junkers Jumo 004 axial flow engines were very unreliable owing to the use of low-grade alloys in their construction, causing regular component failure, which resulted in lots of accidents and thus low airframe availability. The performance advantages that gas turbines offer over reciprocating engines are enormous though, which has led to their widespread adoption throughout aviation lasting to today. Now, operationally, the greatest single cost an airline incurs is in fuel. Therefore, it's crucial to airliner operations that fuel efficiency is at the forefront of design. The problem was, gas turbines fitted to the earliest jet airliners were of the pure turbojet type, which were, as mentioned earlier, extremely thirsty. Now, a compromise between power and fuel consumption just had to be found. Gas turbines driving propellers are turboprops. They're essentially a jet engine coupled to a reduction gearbox driving a conventional propeller. In a turboprop though, the propeller produces the thrust required to actually propel the aircraft, while the hot gases exiting the combustion section are primarily absorbed by the turbines, which drive the compressors and the propeller through concentric shafts. Because of this, turboprops are torque-producing engines, as opposed to thrust-producing engines. Because the propeller produces thrust in a turboprop, there are economic efficiencies associated with their operation compared to pure turbojet engines. But turboprop efficiencies apply at lower velocities than turbojets. Therefore, an engine that combined the propulsive efficiency of a turboprop and the sheer power and performance of a turbojet was an attractive proposition. You still with me? Good. The answer was the bypass turbofan, whose first compressor disc was larger than its following discs and was encased in ducting that directed airflow around the engine core. This airflow bypassed the center engine, hence the name. This big fan at the engine face was driven by a separate turbine and utilized the concept of low velocity thrust produced by a propeller to supplement the high velocity exhaust thrust of a turbojet, offering the benefits of both engine configurations compared to pure turbojet engines. The first production turbofan was the 17,000-pound thrust Rolls-Royce Conway, whose first application was the Handley Page Victor strategic bomber. Compared to the first jet airliner, the de Havilland Comet 1's 5,000 pounds of thrust de Havilland Ghost turbojet engines, the bypass turbofan offered considerable fuel efficiencies combined with greater thrust. It was only a little while longer now that contemporary jet airliners would be fitted with turbofans, and sure enough, in 1956, various airlines placed orders for Boeing 707s and Douglas DC-8s fitted instead with Conways, which offered greater ranges for given fuel loads compared to those aircraft's nominally fitted Pratt & Whitney JT3 turbojet engines. While long-haul routes were flown by four-engine airliners, airlines wanted jet aircraft that could operate on shorter hops, either regionally or internationally, like around continental Europe, where a big four-engine airliner was distinctly uneconomical. A case in point was British European Airlines, the government-owned short-haul carrier that offered domestic services within the United Kingdom, as well as international routes across Europe. They operated the Vickers Viscount, the world's first commercially successful turboprop airliner, and from 1960, the revamped de Havilland Comet 4B. BEA became a trendsetter across the hotly contested intra-European route network.
The name of British European Airways is well known all over Europe.
But its chairman, Sir William Sholto Douglas of World War II RAF fame, required something smaller and more economical than the Comet, with its four thirsty turbojet engines, with a greater performance and payload than the Viscount. Because Sholto Douglas had established a good working relationship with de Havilland, with his decision to actually buy the Comet, he turned to that firm to investigate a jet-powered airliner to replace the Viscount. In July 1956, Sholto Douglas released outline requirements for a short-haul second-generation jet passenger airliner that was faster than the French-built Sud Aviation SE-210 Caravelle twin turbojet, regarded by the British as an upstart competitor. BEA's concept performance was outlined as carrying a payload of 20,000 pounds or 70 passengers up to 1,000 miles at a cruise speed of up to 620 miles per hour. That's just shy of 1,000 kilometers per hour, while weighing up to 100,000 pounds, capable of taking off from a 5,000 foot long runway. It was to be powered by, quote, more than 2 engines. Now, this was a tall order for the mid-1950s, but to fulfill the requirement, the Avro, Bristol and de Havilland companies all hit upon the same idea. Can you guess what it was? A 3-engined jet airliner. It was reasoned that 4 engines for a short-haul jet was just too much, it was uneconomical, while 2 engines wouldn't offer the performance required to meet the demands of Sholto Douglas. Simultaneously, Rolls-Royce was developing a new turbofan called the Medway, a company keeping the theme of gas turbine engines named after rivers in mainland Britain, by the way. Initially, the de Havilland proposal, the DH-121, was to be powered by turbojets, but the attraction of the turbofan held sway, and soon, on paper at least, the DH-121's 3 engines became Rolls-Royce Medways. Now look, this was a time of considerable upheaval in the British aviation industry, which was spurred by Minister of Defence Duncan Sand's notorious 1957 Defence White Paper, which threatened to cancel all manned military aircraft projects and replace them with guided missiles, among other extravagant expectations of an industry actually struggling for orders in the stark post-war environment. The White Paper had repercussions that affected every airframe manufacturer, as they were pressured to amalgamate into 2 aerospace giants, the British Aircraft Corporation and Hawker Siddeley Aviation, as the British government, the primary customer of almost every British aircraft builder, simply didn't have sufficient work for all of them. It was vital for the company's bidding for the BEA requirement to succeed in securing an order. Then, as anticipated sales success that rivaled that of the Vickers Viscount was believed to be just over the horizon for the Victor. In February 1958, after considerable political turmoil brought on by the sudden enforced merger of disparate design offices, the DH-121 was selected as the winning submission, and it was to bear the name Trident. The unique feature of the Trident was the location of its 3 engines. In an aviation first, all 3 of them were clustered around the tail, with 2 either side of the rear fuselage, like the Caravelle, but with its 3rd buried in the very back of the fuselage, and it was fed by a distinctive S-configured ducted air intake, with its opening actually ahead of the vertical fin's leading edge. The 3-holer configuration was born. The DH-121's future was, so the firm thought, sealed. It was to be powered by 3 12,000 pounds of thrust Rolls-Royce Medways, carrying 110 passengers, a maximum takeoff weight of 130,000 pounds, and a maximum range of 1,800 nautical miles. But the apple cart was about to be upset by the very firm who'd actually ordered the jet in the first place. BEA's executives, who'd been closely studying passenger trends, predicted a significant drop in passenger growth going forward. Inexplicably, they concluded that the DH-121 would have to be shrunk to suit their predictions. And most surprisingly of all, de Havilland's chairman, Aubrey Burke, consented to this, and the discussions, described as the most onerous de Havilland executives had ever engaged in, ended with revised specifications to meet BEA's recommendations. This all resulted in a smaller capacity cabin, lower-powered Rolls-Royce Spey turbofans instead of the Medway. Developed from the Conway, the Spey offered a lower power output of 10,400 pounds of thrust, and the Trident was effectively shrunk. Now, in hindsight, this was a catastrophic decision that doomed the growth potential of this rather promising aircraft. On its introduction, the Trident was by far and away the most sophisticated airliner to yet fly, being equipped with many technological firsts, but by shrinking it to suit its specific needs, BEA effectively stymied its chances of export success, relegating it to an aircraft whose promise was cut short even before it had flown for the first time. A paltry 117 airframes were ever built, and it just couldn't compete with a US rival that was on the way. And although that appeared 3 years after the Trident, it went on to become one of the biggest selling airliners in history, with more than 15 times the number of Tridents built. On paper, the Trident looked like a winner. First flying on January 9th, 1962, the Trident 1 could carry 97 passengers in a single-class configuration, incorporating an aerodynamically clean 35-degree swept wing, achieved by the novel clustering of its 3 engines at the tail. Aside from this then unique feature though, its most prominent acclaim was the incorporation of an automated blind landing system developed by Hawker Siddeley and Smith's Instrument Systems. Achieving the first automatic touchdown on June 10th, 1965, the Trident's pioneering blind landing system was immediately successful, and it enabled the imposition of lower landing visibility criteria at airports equipped with the instrument landing systems. The Trident's advanced avionics suite also included a Doppler radar-driven moving map display on the instrument panel, and in a world first, a flight data recorder and cockpit voice recorder. These, colloquially termed black boxes because, well, initially that's what they were derivatives of Australian Dr. David Warren's pioneering devices developed at the Aeronautical Research Laboratory at Fisherman's Bend in Melbourne, my hometown. Refined for installation in production airliners following the Trident's example, this equipment was subsequently mandated by many civil aviation bodies around the world for fitting on airliners operating over their territories. Based on its performance, the Trident comfortably exceeded Sholto Douglas's initial requirements, but its birthing pains, despite its promise, were not over. Before the Trident even flew for the first time, Sholto Douglas had gone to the USA and examined Boeing's TriJet airliner concept, following which he proposed to Boeing and de Havilland that they work together, given each firm's designs closely match one another. This included in engine selection. The initial Boeing proposal was powered by Allison AR-963s, which were license-built Rolls-Royce Spays. Burke went as far as proposing that Boeing build the DH-121 under license, having handed over the company's research to the American firm, which it no doubt accepted with grace and a wry smile. Dissatisfaction with the 5-abreast seating and an exclusively British design approach led Boeing to reject Sholto Douglas and Burke's advances. Boeing was going it alone, and the result would royally steal the thunder of the British trailblazer. Despite Boeing's answer to the Trident becoming one of the most successful airliners in history, the firm was actually initially reluctant to even build a short-haul jet, and the aircraft's gestation was as politically charged as the Trident's. It was largely due to the efforts of engineer Jack Steiner, who, fresh from working on the Boeing 707, was given the task of investigating a short-haul jet. At the time, company executives thought that as the 720 derivative of the 707 had just been launched, they feared that a newer jet would stifle its sales potential, but Steiner believed that an aircraft that wasn't simply a shortened 707 would be more economical, able to operate from smaller airports and challenge turboprops on their home turf, while not undercutting the existing Boeing catalogue. Convincing Boeing was one thing, but the airlines was something else entirely. None of them even agreed on what they wanted. United wanted a smaller jet, but insisted on 4 engines for added safety into airports like Denver, while Eastern rejected a 4-engine aircraft outright, believing it to be too expensive, preferring 2, or possibly 3 engines for overwater flights. Eastern also stipulated that if the aircraft was not capable of flying into New York's LaGuardia Airport, it wouldn't buy it, while TWA strictly specified 3 engines, rejecting 4 or 2 engines outright. Because of these demands, Steiner compromised on a TriJet, but struggled to finalise a configuration. One concept saw an engine under each wing, with the third mounted on one side of the fuselage, which did work aerodynamically but was rejected because of the belief that passengers might balk at the idea of a lopsided aircraft. Ultimately, the configuration of the Trident was settled on. This offered the immediate advantage of a cleaner wing that could be fitted with high-lift devices that were unencumbered by bulky underslung engine nacelles, essential for the demanding takeoff and landing requirements of the smaller airports the airlines expected their aircraft to operate from. In the marketing offices at Boeing, however, a stipulation was made that this new aircraft had to cost no more than $3 million apiece, the cost of a Caravelle, which was eyed warily as a potential competitor. If this applied, Steiner reasoned, the new jet's size would be constrained in the same way as the Tridents had, offering no growth potential. Soon, the suggestion of license building the British airliner, as proposed by the British, was discussed, given the 2 aircraft were shaking up to be carbon copies of one another. Essentially, Boeing had to take a gamble on the project that had only recently been named the 727. Either build a copy of the British Trident, with the constraints that came with that design, or build an aircraft comparable to the company's domestic competitors around criteria that none of the airlines could agree on that may or may not achieve sales success. Not exactly an easy choice. Steiner, however, offered a third option. Through technological advances, he would produce an aircraft that was to change the game for short-haul jets, but it was going to cost more than $3 million apiece. Of course, the rest, as they say, is history. The Boeing 727 was indeed the game changer that Steiner had foreseen. It became the fastest selling airliner in the world, and with a total production run of 1,832 examples, exceeded the demands of the company executives, although each unit cost $4,250,000 at the time of its launch. In the end, that didn't matter. The airlines loved it, the pilots loved it, hell, even the passengers loved it. An unforeseen outcome of the booming success of the 727 was that in 1964, the 60-minute rule was amended to exclude trijets. Such was the faith the government's regulatory body had in the new aircraft. Another, probably less quantifiable reason for its success is that the 727 just looked cool, with its 55-degree swept wing, its rakishly swept vertical fin. It just looked like it was going fast even when it was sitting on the tarmac. It was also one of the fastest airliners actually in service, with a cruise speed that matched transonic jet fighters. Because of its clean wing, loaded with high lift devices on both the leading edge and trailing edges, the 727 easily met the airline's demands for operating into their most challenging destinations, and its 6 abreast seating enabled greater load factors in and out of those smaller airports, thus increasing profits. To facilitate this, Steiner applied the exact same fuselage cross-section as the 707, which enabled the standardization of cabin equipment and layouts. To achieve the type's excellent performance, Pratt & Whitney produced a new engine designed specifically for the 727, the 14,000-pound thrust JT8D low bypass turbofan. Each engine nacelle was fitted with clamshell-type thrust reversers, the side nacelles opening vertically, while the center engine's doors opened horizontally, enabling shorter stopping distances on reduced length runways. Although not fitted with noise suppressors like the Trident, the JT8's bypass air mixed with the exhaust upstream of the exhaust pipe within each nacelle reduced exit velocities and exterior noise. This actually enabled the 727 to overcome the noise restrictions on jets imposed at LaGuardia, and it actually became the first jet airliner to carry out regular operations from there since those restrictions had ever been put in place. A feature that proved useful at airports lacking facilities was an auxiliary power unit in the right-hand main landing gear bay, which enabled independent starting and operation of auxiliary systems without the use of ground power. Another novel feature was a rear-mounted air stair that extended below the vertical tail. After a faltering start with the Trident, thanks to the 727, the TriJet was here to stay. Things were about to get even more ambitious for the type though, as US manufacturers were about to enter another race to build a new jet airliner and once again requiring a new approach to jet engine technology. In this big technological horse race, 2 of the 3 products that were born of this era ended up among the last of the commercial trijets. This time though, it was the military who fired the starter gun for the CX-HLS, or Heavy Logistics System requirement for a vastly more capable heavy lift aircraft than what currently existed. The Pentagon specified a gross weight of 60 tons, with an 8,000-mile range, more than twice the specifications of the Lockheed C-141 Starlifter, the nominal US Air Force heavy lift jet, powered by 4 Pratt & Whitney TF-33 turbofans, which were based on the JT3D, the low bypass turbofan variant of the old smoky JT3 turbojets that first powered the 707s and DC-8s. To power this behemoth, a new type of turbofan engine was needed, the triple-spool high bypass engine. Previous turbofans were configured as twin-spool engines, meaning there were 2 separate compressors driven by 2 separate turbines, whereas the power output demanded by this big airlifter required an engine with 3 separate compressor sections with an even greater diameter first-stage compressor. This of course increased the bypass ratio, that is to say the ratio of the mass of air that flows around the engine's core to the airflow through it. Previous turbofans typically had bypass ratios of 1:1 or 1.5:1, but the big fans, as they became dubbed, had bypass ratios of up to and exceeding 5:1. The benefits that the high bypass turbofan offered over lower bypass engines was greater fuel efficiency, while also enabling even greater thrust at given power outputs. The downside was that these engines were extraordinarily complex to build, they were very big, and they were very heavy. A production version of the engine was expected to have a power output of double that of existing engines, so a nominal output of more than 40,000 pounds of thrust was expected, which at the time was insanely large, given the 727's JT8Ds only put out a third of that amount. The first company to cut metal on its new engine was General Electric at its TF39, while Pratt & Whitney produced the JTF14. It was the TF39, the world's first triple-spool high-bypass turbofan that was eventually selected to power the winning entry in the military's competition. The heavy logistics system had attracted bids from all the major large airframe builders in the US, but beating the preferred Boeing design, Lockheed's cheap proposal became the whopping 840,000-pound maximum takeoff weight Lockheed C-5 Galaxy, which resembled its smaller predecessor, the C-141 Starlifter. Now, we've obviously gone a little bit off topic here from trijets, but the important point is that the TF-39 engine became a big deal, and airlines were staring longingly at it. They saw the potential of the new type of engine and began drafting up requirements for future airliners that were fitted with it. In March 1966, American Airlines released a requirement for a wide-bodied aircraft that would be powered by two of these new engines, carrying 250 passengers in mixed-class configuration across distances of more than 1,850 nautical miles. The aircraft had to be size-limited to enable operating within existing infrastructure at airports around the US, and able to carry its maximum passenger load and 5,000 pounds of cargo from LaGuardia, which introduced previously mentioned operating challenges, to Chicago O'Hare. Over at Boeing in Seattle, buoyed by the high dollar value and predicted market trajectory, executives were thinking bigger and bigger, so design engineer Joe Sutter dusted off the drawings that had been submitted to the military for that heavy lift competition and reconfigured it with a low wing, filling the cavernous hold with passenger seats. That became the Boeing 747. But while Boeing was busy with that, Douglas and rival Lockheed were focusing their energies on the American Airlines proposal. Initially, Douglas investigated a twin-engine aircraft as per American's original requirement, but this soon changed after surveys conducted among potential customers still favoured 3 engines, and that enabled transcontinental range. Over at Douglas's rival, Lockheed's California factory, its executives came to the same conclusion for the same reasons, and they too began designing a TriJet. This decision sparked a rivalry between the two manufacturers that saw two different approaches to the same conundrum: a heavy but cheaper design with room for weight and load expansion, or a more expensive but lighter design incorporating greater technological advances and better basic operating economies than its rival. Which TriJet concept was going to win the appeal of domestic and international customers? Well, fresh from a merger with McDonnell Aircraft, a primarily military aircraft constructor, Douglas had finalised the design of their new TriJet by fall 1967. It was called the DC-10. The new jet was a twin-aisle wide-body with eventual capacity for 250 to 350 passengers in up to 10 abreast seating and high-volume cabin configuration. Its exterior design was striking, with an engine suspended below each of its 35-degree swept main wings, and, most visually distinctive of all, that third engine above the rear fuselage making up the base of the vertical fin in a straight-through tube, a much simpler configuration than the previous TriJets. One aspect of the new jet that operators favoured was its undercarriage. 2 main legs with 4-wheel bogies, a nose leg with 2 wheels, and, uniquely, a 4th leg mounted centrally within the wing box with 2 more wheels. This was the tip of the hat to the future growth potential of the design, enabling load and weight increases. There was even concepts for stretches beyond the American Airlines size stipulations. Sensibly, operators were able to choose which engines were to power their DC-10s, which meant they could continue good relationships with suppliers they'd bought from in the past, a vital component of airline cost and asset management. Meanwhile, over in the sun-kissed Lockheed headquarters at California, the company's attractive L-1011 Tristar was its first foray into commercial aviation since the L-188 Electra back in the 50s. That had been a rocky road with a series of fatal crashes owing to design defects, so everyone at Lockheed was keen not to replicate the same pathway the Electra took in developing the company's first commercial jet airliner. Resembling the DC-10 in general appearance, the Tristar's passenger capacity was similar to its multi-class configuration of 250 in a wide-body, twin-aisle fuselage. Its engines were mounted in similar fashion as the DC-10, under the wings and in the tail, but the Tristar stuck with the tried and true TriJet layout of the engine being buried aft of the rear fuselage and that big S-duct feeding it, visually distinguishing it somewhat from the Douglas jet. When it came to engine selection, Lockheed tightened the reins. The technologically innovative Rolls-Royce RB-211 triple-spool turbofan was exclusively selected to power the Tristar, a curious decision that actually eventually hampered its purchase appeal. Although US engines were considered, fitting them to the tail would have required the redesign of the S-duct. Lockheed was backing itself into a corner, and financially, it began to strain the company. Once they'd finalised the design, Lockheed executives were confident their jetliner would win the American Airlines order, so they were devastated when, in February 1968, the airline announced that it had chosen the DC-10. This was a huge blow to Lockheed's confidence, as the company, not for the first time in its history, was on the verge of bankruptcy because of the Tristar. But salvation came in the form of some 144 orders only a month later, which was enough to set it into production at Lockheed's new factory at Palmdale. The Tristar, it seemed, had been saved, and Lockheed was temporarily out of hot water, but the development of the Rolls-Royce RB-211 had put the company into bankruptcy, resulting in a government bailout. This was an ominous portent for the cash-strapped manufacturer so early into the aircraft's development. That aside, this big order was good news for the Lockheed board, many of whom understood the risks inherent in branching into the airline industry, as fickle as it is, especially given the company's precarious financial situation. At least with military orders, there was always a guarantee of a paycheck, whereas unexpected environmental shocks tend to wreak havoc with airliners who are so dependent on the vacillating needs of the travelling public. One such shock, though, was just around the corner in the form of a global oil crisis brought about by war in the Middle East. It was to send the cost of crude skyrocketing, resulting in rising petrol prices around the world. Suddenly, as the 70s dawned, that uncertainty resulted in spectacular falls within the airlines as they nervously cancelled orders for new aircraft that had looked so promising just a year or so earlier. For McDonnell Douglas and the DC-10, the bad news actually worked in their favour. While airlines did demonstrate restraint, the more affordable TriJet won more orders than its more expensive rival as the decade progressed, while the Tristar was even further hampered by its basic design. Remember that little extra undercarriage leg fitted to the DC-10? Well, that enabled even greater weights to be carried across greater distances than the Tristar, which, as sophisticated as it was, couldn't match that DC-10's long legs. The Tristar was designed as a continental USA spanning aircraft that was lighter and more fuel efficient than the DC-10, but the DC-10's load carrying capacity completely outshone the Tristar's because of that middle leg. Realising they were being beaten in the sales game, Lockheed's designers proposed fitting the Tristar's main undercarriage with a 6-wheel bogie, but this necessitated redesigning the entire wing box to accommodate the bigger gear. A central leg, it seemed, like the DC-10's, was completely out of the question, requiring just way too much structural redesign, so a new inboard wing section was conceived, but no one was actually interested in buying this version, and sadly, a truly competitive Tristar to the DC-10's sales supremacy never actually appeared. And this was after a disaster-ridden first decade for the DC-10, as several high-profile air accidents resulted in the aircraft's grounding by the FAA in June 1979, following the loss of an American Airlines aircraft after takeoff from O'Hare in May, killing all 271 people aboard and 2 people on the ground. Worse was to come, as later that year, on November 28th, an Air New Zealand DC-10 flew into the side of the active volcano Mount Erebus during an Antarctic scenic flight, killing all 257 people on board, rounding off a dreadful decade for the Douglas three-hauler's reputation. Despite these terrible tragedies, though, the DC-10 did remain a steady performer into the 1980s, even in the face of the astonishing sales superiority of the Boeing 747 and the burgeoning quantity of twin-engine jets that began to flood the market. This meant that, ultimately, the DC-10 was a greater sales success than the Tristar, with 446 being built. The final example rolled out of the factory in 1989. It has to be said, though, this was less than half of the 1,000 sales predicted by Douglas executives. By contrast, only 250 Tristars were built. Lockheed chose to cut its losses and draw the curtains on building commercial aircraft totally in 1984, in what had been an excessively expensive failure to match its nearest rival. Despite this, however, the elegant Tristar is often hailed as one of the most beautiful airliners ever built. Lockheed were good at that. These two fierce competitors weren't the last American trijets, though. The McDonnell Douglas MD-11 pushed the boundaries of what the DC-10 could have been from the outset. Its fuselage was stretched, enabling even greater load-carrying capability. But it was too little too late for this warmed-up DC-10 with winglets. With the advent of longer-range twin-engine aircraft concepts in the early 1980s, extended twin-engined operations, or ETOPS, the successor to that old 60-minute rule, were extended across even greater distances between the diversion airports, especially by far-flung operators like Air New Zealand and Qantas at the bottom of the world, whose jets had to cross vast stretches of ocean to get anywhere. New twin-engine aircraft from European manufacturer Airbus, once regarded as a joke by the big American firms, were turning the tables on the solid sales the DC-10 and Tristar had previously enjoyed. And once Boeing launched its new generation of medium and long-haul airliners, the 757 and 767, the end was nearing for the trijets that were populating the world's carriers. Even the old king of the trijets, the 727, was being outsold by its little brother, the 737. The suddenly outdated-looking MD-11 continued to struggle on, as it was unable to meet its advertised range and speed figures, souring its appeal among airlines. On top of all of that, though, Boeing had an even bigger surprise waiting in the wings for the trijet. The 777 concept was to bridge the gap between the 767 and the 747, exactly where the poor-performing MD-11 sat in terms of capacity, launching a new approach to airliner design that saw operators consulted across every aspect of the new aircraft's conception. Suddenly, as the century neared its end, the trijet was going the way of the dodo. Now, I haven't included the Soviet-era Tupolev Tu-154 in this analysis, owing to the remoteness of the Soviet airline industry from the rest of the commercial world, but it was born of the same considerations affecting the Soviet air travel market as those affecting the rest of the world. Although the Tu-154 was unique within the market it operated, remaining relevant until the end of the Soviet Union and the advent of more advanced and commercially viable Western designs operating from former Soviet states. So that, ladies and gentlemen, is the story of the rise and fall of the trijet, a design trend that seemed to be everywhere in the 60s, 70s, and 80s, with its origins back to the 20s, but whose time ended as quickly as it had arrived. The trijet certainly added uniqueness and flair to aircraft design, and born of technological innovation, was brought down by the very thing that enabled its creation in the first place. New jet engine technologies and legislation changes gave birth to the trijet, but those same advances and relaxing of the rules didn't let up, effectively ending its reign. Today, trijets are still in limited service, mostly cargo-carrying MD-11s with the likes of FedEx. But tantalisingly, Airbus filed a patent in 2008 for a bizarre-looking thing with a twin tail and, you guessed it, 3 engines. Now obviously, there's some experimental interest in 3-engine aircraft like this, but it just doesn't seem likely that concepts like this will go anywhere. And, for the time being at least, the age of the trijet is well and truly over.